Right, let's have a look at section 10.2 out of your text, page 278, and the topic in this case is distance and displacement. Now I mentioned that in the previous section 10.1. I said one was a scalar, which was distance, the other is a vector, which is displacement. So I want to go through that again, but I want to look at distance and displacement first, because they're the fundamental quantities, physical quantities, when you talk about motion. Now you measure distance, and then the next thing to measure, or displacement, distance and displacement, the next thing to measure after that is how fast you change your displacement, which is called velocity, and then we talk about how fast we change velocity, which is then called acceleration. So they're the three parts of our work. So this is the first part, the first physical quantity we'll look at. Now distance is just a measure of the total length of the path taken. So you've often seen treasure maps where, you know, they'll say you start here and the treasure is here somewhere, and they'll say take a few steps this way and a few steps that way and a few steps and so on. Now the distance is, if you add up all of those lengths, that's the distance you walked or you moved. Now for instance, if you're going to the shops, you might walk up one street, turn the corner and keep going all this sort of way. So the distance is the path taken. So let's say, for instance, I'll do this as a simple demo. Let's say I'm starting here. I'm now going to walk a metre. Now I can't really fit a metre in here very easily, but imagine I was in our lab and I was doing it this way and I got the full length of the board. But let's say I went this far and I've moved a metre. So I've gone a metre in that direction. Now I've moved a distance of a metre, so the distance is 1 metre, the displacement is 1 metre, in this case it's north, but let's say it's plus 1 metre. Okay, so they're both the same, except displacement has a sign to indicate its direction. Now I could walk another metre and be here, so my distance travelled is now 2 metres and my displacement is now plus 2 metres, okay, heading in that direction. Now if I do this, let's see if you can get the hang of this. I'm starting here at the 0, the origin again. Now I'm going to walk a metre. I've now walked 2 metres and I'm coming back a metre. Now the question is, what's my distance and what's my displacement? Well, my distance is 2 metres and I've come back a metre, so it's 3 metres. Okay, so what's happened is I've started here, I've gone 2 metres, and then I've turned around and come back to there. Okay, so that's 1 metre, 1 metre, 1 metre. So my distance is 3 metres. Okay, now the symbol for distance is just D. Now I think you would have learnt that in grade 10. You might have talked about displacement and used a D as well, but we save D for distance. It's basically the first letter of the word distance. Now my displacement, I started there and I went all this way, I went 2 metres and I came back to here. My displacement is my change of position, so I've gone from there to here. Now my change of position is just 1 metre and it's in that direction. So basically I've gone from there, this is the start and this is the end, so my displacement is just 1 metre. So displacement equals 1 metre. Okay, now I need a symbol for that. We've already used D for distance and it's a bit tricky, but I just tell my classes we use this symbol here, the S, and so it's called S. That's not the real reason. There is a Latin word meaning motion that starts with an S, but I just tell them that, and then of course the students say to me, well, this has got an S in it. Yeah, well that's just too bad. So they're both S's. One's a D, one's an S. Okay, so the distance is the total path travelled. So what you could note is that distance is D, total path travelled. Now you'll hardly hear the word distance throughout our work on linear motion. We always talk about displacement. this is the change of position. Okay, and that's the difference. So the change of position is just the 1 metre. Okay, so that's the first point, the difference between the two. This one is a scalar and this one is a vector, of course, because, oh, I forgot to write this in. Look, displacement is plus 1 metre. Okay, or I could have said 1 metre north or west or whatever. This doesn't have any direction in it. It's magnitude only. So the 3 is the magnitude, the 1 is the magnitude. The M is the symbol for the unit. Now that stands for metres, of course. This is nothing new to you, but there is a symbol for the units, which is the M. The units are actually metres. The unit is metres, the symbol is M. Okay, the quantity is displacement, the symbol for the quantity is S. So you've got a quantity symbol, unit symbol, M, and there's the name of the unit as well, which is metres. Okay, let's get rid of this and move on to the next thing. Let's talk about addition of vectors. Now, say for instance you're on a bus and the bus is travelling at 10 metres per second. Now I'm using these symbols here. I might as well get you used to it right from the start. That just means metres per second, or if you like, metres over second. Now you know from maths that these are to the power of 1, and if they're to the power of 1 you usually leave them out, so you can just leave it out like that. But you also know that if you bring the denominator up to be up beside the numerator, you have to change the sign to its opposite. So that was s to the power of 1, that becomes s to the minus 1. So velocities are done as ms to the minus 1. It just means the same as that. Now so this is the bus. So let's say the bus is travelling along the road at 10 metres per second, but let's imagine you're on the bus. Now let's say you can walk at 1 metre per second relative to the bus. So this is the bus, this is you. You can walk at 1 metre per second relative to the bus, and the bus moves at 10 metres per second relative to the ground. Now what you'll notice, I've used these arrows. I should have mentioned this earlier. One way of indicating a quantity or representing a vector quantity is with an arrow. Okay, so they're called directional arrows, which, you know, there's just an arrow head indicating the direction. Now the other way to do it would be, so I'm writing v equals 10 metres per second. The other way to indicate a vector is to put a little arrow above the symbol. So there's two ways of indicating a vector, using a vector arrow or a little symbol above the v, and that's that little symbol there. It's like an arrow with a half head on it. Now some books will do it like this, they'll do a full arrow. Other books will do it with a little squiggle on the top, and what you can do in a textbook, but it's hard on the board, is to make it in bold. So sometimes you'll see in the text I've done some symbols in bold, indicating that I want you to think of them as a vector. Now a lot of times they are vectors, but we just don't put them in bold because the vector nature of it's not so important. Okay, so just different ways of representing it. Now can you imagine if you're on the bus moving, and you can move at 1 metre per second that way, and the bus can move at 10 metres per second that way, your velocity relative to the ground is the sum of these two. Okay, because you're moving at 1, the bus is moving at 10, so you're moving at a total of 11 to the ground. So I'll just write this in here so it's pretty obvious. This is u relative to ground. Okay, so this is bus relative to ground. This is u relative to bus, and so on. Now another good example of this is with cricket. Say a cricketer can run at 10 metres per second and then delivers the ball at 1 metre per second relative to himself or herself. The speed of the ball will have the speed of the person bowling it plus the speed of the ball relative to the person, and it'll go at 11 metres per second relative to the ground. Okay, now the way you do this with arrows is you just put the two arrows down and you put them head to tail. So addition of vectors, when you add them, you put head to tail, and basically all you do is you start at the tail of the first arrow and go to the head of the second. So the final would look like this. Okay, so this is called your resultant. So it's basically the sum of those two, and we often put a double-headed arrow on it like that to indicate it's the resultant. Okay, so that's pretty straightforward. The second thing, so you'll get heaps of that. Now say for instance you had, look, I'll get rid of this. I'll just give you another example. Say for instance you had an object sitting on a table, such as a train or a block of wood, but we could be talking about a train on the ground. Let's say there's a engine pulling this carriage along, and it might be applying a force of say 1,000 newtons that way. So we could say plus 1,000, or we could say that arrow is representing this 1,000 newtons. Okay, now let's imagine there's some friction. Now friction will act in the opposite way. Okay, so you'd subtract them, and that's the topic for this next little bit. I just want to do one more example before we get on to subtraction. But let's say you had something pushing it from behind as well. Now often with really heavy coal trains, you'll see these things, you know, hundreds and hundreds of metres of coal carriages long, and they'll have an engine on the front and an engine on the back. The engine on the front will be pulling, and that'll be more than 1,000 newtons. It'll be hundreds of thousands of newtons, but let's imagine. But you'll have one on the back, and let's say it's 1,000 newtons as well, pushing that way. So the resultant force is merely the, I better make them the same length, that 1,000 plus that 1,000, and you draw a line like this. You say the resultant is 2,000 newtons. You could put a plus, or you could just use the arrows. Either way, no, you put both if you like, it doesn't matter. Okay, let's try subtraction. Now, I just talked about the train. Let's imagine, we'll call this subtraction. Now, let's imagine we've got the train again, and there's the track, and let's say we've got 1,000 newtons pulling it that way. But let's imagine in this case we've got friction, and look, I'll put a F. That's F for the, we'll call this FA. We do this in grade 12 basically, which will be your unit 3 at the end of the year, just after the end of term 3. So for when you do term 4, we'll be using terms like A. That stands for applied. So the applied force is 1,000 newtons. Let's say we've got a force of friction back here, and I'll call it little f. So that's the force of friction. We always use a capital F for the quantity we're talking about, and you use all these different subscripts to indicate the type of force. So you can have an applied force, you can have a tension force. Now in physics we'd call a tension force Ft. Sometimes in maths you might find they just call it capital T, and they might call this A or something like that. It's just a little convention. It makes no difference to the calculations, but it's just different ways of doing it. So let's imagine the friction, oh I don't know, let's call it 100 newtons in that direction. So that'll be a negative, and this will be a positive. Okay. Now we're going to, oh hang on, this is not subtraction, this is This is still addition. Sorry, rub that out. This is still addition. I'll mention attraction in a minute. This is an example of addition where they're actually moving in opposite directions. So basically everything's the same. We've got 1,000 newtons this way, so that's plus 1,000, or just 1,000 that way. Now the friction is in the opposite direction, but you still do them head to tail. So head to tail, and you put it like this, okay, and that's 100. Now I don't have my lengths right here. That should be 10 times that, so it should be something like that. We can make that smaller. Okay, the rule is you start at the tail of the first one and you end up at the head of the second one there. So you have a straight line that looks like that. So this is your resultant, and if you think about it, it's 1,000 minus 100, so this is 900 newtons in that direction, which is positive. Okay, so I misled you at the beginning when I said subtraction. I thought I better do one of these additions where you have the forces or the vectors operating in different directions. It's still an addition. You're adding the two forces to get the resultant. Okay, so that's all pretty straightforward. Let's look at subtraction now. Now, subtraction's a tricky one. Say for instance, I said to you, now without giving you a practical example, let's just have a look at how you might do it mathematically or using vectors. Let's say I had a vector like that, and I wanted to subtract, let's say this. I think this will work. No, yeah, this will work. Okay, say I wanted to subtract that. So it doesn't matter. Let's say this is 1,000 again, and let's make this 400. It doesn't matter if it's newtons or whatever, it's just some sort of vector. Now the question is, how do we do a subtraction? I'll talk about when you want to do a subtraction later, but how would you do a subtraction? Now you have a rule for addition. The rule for addition says you place them head to tail. Now the question is, what do you think you do for a subtraction? Now you could say you either place them tail to tail, or what we do in the text, and I think it's much easier, is you turn this subtraction into an addition. Now you know in maths you could say 1,000 minus 400 is the same as 1,000 plus negative 400. Okay, it's the same idea, it's just the way you've got your signs arranged. And this would equal 600, this would equal 600. Okay, we're going to use the same sort of process where you turn the subtraction into an addition, but you change the symbol or the sign of the second quantity into its negative. Okay, so in this case what you do is you'd have it's equal to, I'll get rid of this as well, we don't need that now, this is subtraction, so it's that plus the negative of that. Well, if that's 400 that way, that's the positive value, the negative is just 400 this way. Okay, so it's still the same magnitude, it's just opposite directions. Now when you put those two together, you get this, 400, 1,000, and you start at the beginning there, start at the tail of the first one, and you go to the head of the second one, and if you work that out, it's 600 plus, okay, because it's in the positive direction. So the idea for subtraction is to make it an addition by reversing the sign of the second one. Now the question is, when would you do subtraction? Almost none of our work in, it's done with forces, but most of this work on subtraction will come in Unit 3 at the end of the year when we do circular motion. There's a particular question about an object spinning in a circle where you have to do a subtraction of vectors. I won't go through that one now because that's in 2 dimensions. like I said, grade 12, unit 3 is motion in 2 dimensions, that way and that way, or in the case of horizontal motion, you've got motion that way and you've also got some motion this way. Okay, but you meet subtraction in some places. Look, you've met it for temperatures. You know that temperature, now temperature is not a vector quantity, it's a scalar, so you know it's this. So a change in something, whenever you have a change in some physical quantity, it's final minus initial. Okay, now that's a subtraction. So if you do it in linear motion, you'd have to treat it as a subtraction and then change it to an addition. So say for instance I said, what's the change in velocity of an object, say a ball? You'd say delta V equals V final minus V initial. Remember, it's always final first minus initial. Okay, let's say for instance we had one. Let's say you had a ball. No, I had a ball here. Let's imagine you've got a wall here. So there's a brick wall, and you shoot, or you throw a ball at it, hits the wall, and then bounces back. Now some of its energy will be lost because there's energy losses in the collision with the wall. There's heat losses and sound. So let's imagine you threw the ball that way at, say, 10 meters per second. Now that's in the negative direction, so this is V initial. So I'm making the initial direction negative. It doesn't have to be. I could put the wall over here and throw the ball that way. This is just a simple one. This is really worked example somewhere in 10.2, probably worked example 10.2a or something. The numbers might be a bit different. But let's say it rebounds off the wall, so it hits the wall and then rebounds, and its V final, let's say, is 8 meters per second. It's slowed down a bit because it's lost some energy. Now this will be plus, okay, because it's in the positive direction. If I said to you, calculate the change in velocity, whoops, no question mark, calculate the change in velocity, you just do a simple calculation like this. Okay, so you'd have V final, which is 8 meters per second, in the positive direction. So that's 8 in the positive direction. I'll make it a bit bigger. And minus the V initial. The V initial was 10 that way. Okay, so the change in velocity is just the subtraction of those two. Now look, I'll get rid of this because it's in the way, and what you do is you want a subtraction. So I'll just, it's time to use some green. So we've got final plus that. Remember we've changed it to an addition, so we have to change the sign of the second one, the initial one, to its opposite. So if you like, that's plus 10. Okay, it was 10 this way, so if you like, that was negative 10 and that was plus 8, and now I've reversed the direction of that, so it's plus 10. And so you'd write those two down together, that, so you've got 8 and 10, and the resultant would just be that double-headed arrow, 18 meters per second, okay, in the positive direction. Now you might think, hang on, we're subtracting. How can subtracting 8 and 10, or subtracting 10 from 8, be 18? But it's the direction that the ball is heading. Okay, it's going in one way and then it's going back in another way. If you're taking away two that are in the same direction, of course you wouldn't get that. I needed to show you that because this idea of subtraction and change in velocity is pretty important for working out acceleration. Okay, so I'm going to leave that with you. I think that's about it. Oh, one other thing I meant to mention. This is pretty straightforward. So this is multiplication of vectors. Okay, so say for instance you had that vector there, let's say it was 3 newtons of force, so F equals 3 newtons that way. If a question said the pushing force, instead of being 3 newtons, a force of say 10 times that, no, let's not make it 10, twice that was applied. So it'd be like this. So if you multiplied that by 2, you just have a total of plus 6 newtons. Okay, nothing tricky in that. So you can multiply a vector by a scalar, if you like, by just that numeral, and you just multiply the length of the arrow, or in the case of the numeral, you just 3 2s are 6, and that's it. So multiplication is pretty simple. Division would be the same sort of idea. You don't need much of this in the senior physics, so that's about it. Now I think I've done that. There's a CYL 10.2, page 281, worth trying. So we've finished 10.1, 10.2. It's all pretty straightforward stuff. It starts to get a bit heavier in the next bit of work. So you should have got through that on the Tuesday, and then Thursday I think we've got the double. We'll continue on with some of the graphing and formulas. That's when it starts to get a lot more complicated. Okay, I'm going to leave it there. Thank you.